proof of Cauchy's repeated integration formula. And the proof is insanely beautiful, and it's by induction, and like it invokes a lot different ideas. And yeah, I really love the proof. Okay, so first of all, let's discuss what Cauchy's repeated and integration formula is. So over here, notice that what's happening is, let's say first of all we have some function, right? Function of any variable. We can, let's say, g sub n, so that when there are lots of variables, we can actually name them n-1, n-2, right? It's just for convenience. So we are first integrating this function, right? And let's take the base point a and up to so another variable. So basically this is just another variable, right? So we integrate it, we get the antiderivative, and again we again take this integral. Now this will be a function of g sub n minus 1, right? This a is just constant, so these g are variables. And again, if we integrate this with g sub n minus 1, right? Integrate this, and again let's take the base point a, and then again another variable g sub n minus 2, right? Now again this whole thing will be a function of g sub n minus 2. Again integrate with respect to g sub n minus 2, again from a to g sub n minus 3, and just go on like that, right? And then yeah, so finally, okay, now this is function of g sub n minus 3. So if we integrate it, like let's say up to dz1, and then this is from, okay, maybe let's say if it's dz2 and you integrate from a to g1, right? Now after that you again integrate with respect to d sub g1, and now finally the last one could be some really another variable, right? Let's say x, right? Okay, now this will be some function of x, right? So how we denote this is, so basically it's if let's say we have derivative of some function, we denote this as, like, let's say first derivative or second derivative or something like that, right? So but if it's integral, we represent by like first integral, or let's say second integral, or so on like that. So over here there are n integrals, right? So that's why we can denote this as nth integral, and then this is a function of x, right? Because the last variable, when there's the last integration happens, and then we have it in terms of a and x, so this is a function of x because a is a constant, right? Okay, so now what Cauchy's integral formula says is, this whole like repeated integration n times this like n antiderivatives, these will just be equal to this formula, 1 by n minus 1 factorial integration from 0 to x of x minus t to the power n minus 1 f of t dt. So this whole thing, n antiderivative, is compressed to a single integration, right? And like, yeah, this formula is also used to like define fractional integral, right? Because now if you have this formula, you can just substitute n as any fractions, right? Like, I mean, numbers which are not integers, and this integral, it still makes sense, right? Even though the like fractional number of integral doesn't make sense, but this one makes sense. So that's how you can define like fractional integral. And also, let's say if you put n as negative numbers, you can define fractional derivatives, and that's why this formula is actually a lot helpful. And yeah, that's why we are gonna put this in this video. And our proof will basically be proof by induction, right? So the statement we are gonna prove this is, let me write it properly now, a to x, a to z1, up to a to zn minus 1, and this is f of zn, dzn, dzn minus 1, up to dz1, and this will be equals to 1 by n minus 1 factorial integral from a to x, x minus t to the power n minus 1, f of t dt. So yeah, when like if you want to have n as real number, you can basically write factorial as gamma of n, right? Because gamma of n is defined for any real number, whereas the factorial is for natural number, right? Okay. So now we want to prove this, right? So we want to prove by induction. I guess you guys know how proof by induction works, right? So let's see, if we are given a statement like for any n, what we do is we first prove like p of 0, right? When n is 0, and then assuming p of k is true, we will try to prove that p of k plus 1 will also be true. If this is true, this will also be true. And if that's the case, Like, because P of 0 was true, that implies P of 1 will be true, that implies P of 2 will be true, that implies it will be true for n being any natural number, and that's why it's true for all n. So that's how proof by induction works. So over here, our base case will not actually be n equals to 0. This will be n equals to 1, and then, yeah, and then we can prove that it will be true for all natural number greater than 1. So let's see. Basically, this by P, I actually mean this entire statement. I can call this P of n, right? So P of 1, if I need to prove this just means that, okay, so now over here, notice that this integral is up to g sub n minus 1, right? So n is 1, that means it's up to g sub 0. So g sub 0 is actually just x. So over here, a to x, and then over here, g sub n. So I mean that will just be g sub 1 in this case, and then dz1, just dz1, right? Because like it's up to dz1, right? Last variable. So this should be equal to 1 by 1 minus 1 factorial, which is 0 factorial, and the integral from a to x minus t to the power and 1 minus 1 is 0, f of t dt. So our LHS is a to x, f of g of 1 dz1, and then this is the 0 factorial is 1, a to x minus t to the power 0 is just 1, and f of t dt. Also in the left hand side, I can actually write this g1 as anything, right? Because that's just dummy variable. So I can say that this is just f of t dt. And yeah, that's how we can see that both sides are actually same, right? So P of 1 is proved. Now what we do is we assume that P of n is true and try to prove P of n plus 1. Okay, so assume and to prove, right? So let's see what we're assuming. We're assuming that this integral over here, a to x, a to g of 1, up to a to g sub n minus 1, f of dzn, sorry, f of gn, and all this up to 1. This is equals to 1 by n minus 1 factorial, a to x, x minus t to the power n minus 1, f of t dt. And what you want to prove is a to x, a to g1, and now at this time this actually goes up to n plus 1, right? So if you substitute n plus 1, so this should be g sub n plus 1 minus 1, which is n. And over here this should be g sub n plus 1, dz sub n plus 1, dzn up to dz1, right? So right now there are n plus 1 integrals, okay? Initially there were just n integrals, but now n plus 1 integrals, and this should be equals to 1 by, substitute n as n plus 1, so that becomes n factorial, a to x, and then x minus t to the power, this becomes n plus 1 minus 1, so n f of t dt. We need to prove this statement, right? Okay, so let's see how we're gonna prove it. So let's take the LHS. So a to x, a to g1, up to a to gn minus 1, a to gn, f of gn plus 1, dzn plus 1, dzn up to dz1, right? Okay, now if I group the n integrals inside, I mean with excluding the first one, so there are just n integrals now, right? And in this case, we know what to do. We know the formula, right? For n integrals, we can use the p of n, right? So that's what we are gonna do. We're gonna use the fact that we have assumed we have assumed. Okay. Now using our assumption, we can now write this as 1 by n minus 1 factorial, and then integral from a. So in this case, the variable that we refer by x over here is the first variable, and in that case, the first variable is g1, right? So this will be g1 minus t by n minus 1 f of t dt, right? And after this, we have dz1 over here. Yeah, I can actually take the 1 by n minus 1 factorial out, right? Integral from a to x of integral from a to g1, g1 minus t by n minus 1 f of t dt dz1, right? No, there seems to be a little bit of problem because we need to integrate something, this expression, and we don't know the function, and there's also product of two functions, right? So yeah, in T, there's actually a product and also unknown function that makes it hard to integrate. But actually, notice that over here in G1, there's just a single function. And it seems like maybe it's easier to do the outer integration before the inner integration. And turns out that's the case. So yeah, let me just state it for now and then I'll prove it, right? Okay, actually, this thing over here, the integral of this entire expression with respect to G1, that just turns out to be integral from A to G1 and then G1 minus T to the power n by n and then f of t dt. So this turns out to be actually the integral of this function, right? And then I will actually prove this. And how I will be proving it, I will basically take its derivative with respect to g1, right? And then I will show you that this expression will actually be equals to integral from a to g1 of g1 minus t to the power n minus 1 f of t dt. Even though over here it looks like I'm just taking the end derivative of this expression, but that's not really the case. It's just a coincidence over here. Like, it's not necessary that always it will be in this way, right? But yeah, in this case, that's the case. Actually, maybe that's true if these were all some different constants, but over here, this is again a function of g1, so that need not necessarily be true. But yeah, we'll prove that. And to prove that, we need to take a little bit of detour, right, into the this thing called Leibniz integration formula. And then from there, we'll be able to prove this fact. And if once you're able to prove this fact, this thing, this statement will be super simplified. Yeah. So let's just prove this fact. And to prove this fact, let me first tell you something called Leibniz integral formula, and then yeah, we will be basically done. So okay. So what's Leibniz integration formula? Huh. Okay, so what this states is, let's say I have some integral from a of x to b of x, and let's say some function of x and t dt, just like over here, like this is function, this entire expression is function of g1 and t, right? So I'm just trying to write it as x for now. And then if I'm trying to, let's say, take derivative with respect to x, so what will this be? So that's the formula, but yeah, let's see how we get that formula. Okay, first of all, if you just try to use just normal ideas, we know that this over here is integral of g with respect to t, right? So yeah, integral of g, let me denote the fact that this integral is with respect to t, not with respect to x, because the integral of g with respect to x and t can be different, right? Because it's kind of partial integration, you know. So yeah, let me denote this in this way, like integration with respect to t, and then x comma t, and then a of x, b of x. So yeah, t goes from a of x to b of x, right? Okay, so now I'm trying to obtain a formula actually, okay, and I'm just trying to see how to make sense of that. Okay, now this will actually be integral with respect to t of x comma b of x minus integral with respect to t of x comma a of x, right? So now we want to differentiate this with respect to x, right? And notice we see that both of these are actually functions of x now. So what you gotta do is you gotta use the multivariable chain rule, right? So first of all, you just differentiate this with respect to x, and then you just differentiate this. I mean, you just differentiate this with respect to first with the first variable, how much does the first variable contribute to the derivative, and then the second variable. So how it works is, let me show you. So first of all, when you are just invoking the first variable, so what you will have is derivative of this function with respect to x, right? And that's it. And plus, when you are trying to compute the derivative with respect to the now second variable, right? So over here, notice that this was actually t, right? So what happens is if you take the derivative, you will just get back t because that's where you had t. Now, if you take derivative with respect to b of x, that just goes to t. I believe this would have been more easier if I gave you the actual chain rule, because it seemed like I'm not being good at explaining things. So let me just give you the chain rule first, and then I'll explain more about this. So let's say if you have to find the derivative, and this function over here, let's say if it's function of uh, p of x times q of x, how this actually works is, so first of all, you have derivative of g with respect to p, right? And I should actually write a partial over here with respect to p, and then you have derivative of p with respect to x, plus, and then you have derivative of g with respect to q, and then you have q with respect to x. So that's how multivariable chain rule works. And now, yeah, that you have seen this, now it should make more sense. First of all, I'm taking derivative with respect to x, and this is the first part, right? And then derivative of x with respect to x is just 1, so that's why I'm not writing anything over here, that's just 1. And now, with respect to q, so because this is variable is actually just substitute for t, if I differentiate with respect to b of x, I get the original g of x back, right? And then I will have derivative of b with respect to x, so that's b prime of x. I think it made more sense now because I gave you the multivariable chain rule. I'm gonna erase it from now. Maybe keep it because yeah, you might need it. Okay, and after that we have the negative sign and the same thing over here. So first of all, you will differentiate this with respect to just x, and then x comma this is a of x, and then after that you will differentiate with respect to a of x, but then you will get z because this was basically just t, right? And if you differentiate with respect to t, you get the original function back, and then x comma this will be a of x, and then derivative of a of x from here, that becomes a prime of x, right? And so now this becomes you have g of x comma b of x, b prime of x, minus g of x comma a of x, a prime of x, plus you have this integral with respect to t but partial with respect to x comma b of x, minus this thing, x comma a of x. And actually you can write this in a different way, the last thing, in the following way: g of x comma b of x, b prime of x, minus g of x comma a of x, a prime of x. And then you go, how we can write it is, because these two are like the limits where t goes from, right? So you can again write this as from a of x to b of x, and then derivative of g with respect to x of x comma t, right? That makes sense because you just get the same expression if you integrate this expression. So yeah, so that is actually the formula, and I was trying to give you the idea, so it took a long time, but I think it makes more sense now. Even though I definitely complicated things at some point, but I think it makes sense now. X comma a of x, a prime of x, and then plus integral from a of x to b of x, just so x of x comma t dt, right? Okay, now that you have this formula, let's try to prove our previous claim, right? And maybe I should just erase this all for now because I need some space over here. So if I erase this all, this whole thing, okay. So now over here, we want to prove this expression, right? So this expression, right? Because once I prove this, then it will be super easy. Okay. Yeah, so once I prove this, we can simplify this a lot, as I've already told you, right? So yeah, maybe I should keep that. Okay, but this needs to be simplified. Let me just mark it, just in case I forget it. Okay, so now let's say how we can use this formula. So over here, so this is basically our z of x comma t, right? So now we know that how we need to use this formula. So if we use the formula, let's see how it goes. Over here, x is basically z1, right? So do remember that. So d dz1 of a to g1. A is a constant and g1 is a variable. G1 minus t to the power n by n f of t dt. Now this will just be, first of all, g of x comma b of x, right? So our g is this, I told you this is the entire function g. So we will have x comma b of x. X is just g1 and b of x in this case is also g1, right? So we will have g1 minus g1 to the power n by n, and then I already told you that like in this case yeah, okay, wait. So in this case g as a function of x and t, so we see that in place of t we are writing b of x, right? So that's why I wrote g1 over here, and our b of x was actually g1, right? So now our t is also g1 because I already showed you that over here in place of t we are getting b of x over here, right? So this becomes now f of g1, yeah, and then and then b prime of x, since our b of x is just t, our b prime of x, so basically will just be 1, right? Am I in a good direction? Because I'm myself getting confused at this point. So yeah, just to clarify, in this case, our over here the where we need to have g of x comma t of b of x, and then basically wherever we had t, I'm writing b of x, and in this case b of x is g1. So it makes sense to write g1 over here, and then when I'm taking b prime with respect to x, so this prime was with respect to x, right? And then so what's our b of x again? B of x was g1 and x is also g1, so that should be 1. Yeah, now it makes sense. I'm sorry guys, but yeah, there's a lot of things, so yeah, it kind of getting complicated. Now we have g of x comma a of x, right? Now a of x is actually a, right? So in place of t, I'm writing a of x, which is a. So we will have g of 1 minus a to the power n by n, and then yeah, just as I said, in place of t, we have a of x, which is a. So we have f of a. Now a prime of x. So we know this derivative is with respect to x, right? And x is our g1. So we have derivative of a with respect to g1, and that's just 0, right? Okay, it's making perfect sense now. And now integral from a of x to b. Okay, now a of x is again just a, b of x is g1, and over here our again now g prime of x. So that means our derivative is with respect to x, which is g1 in this case, right? So if we take derivative with respect to g1, so what we will just have is n times g1 minus 2 to the power n minus 1 by n, right? And then yeah, all these things will be as it is, right? Okay, so now over here, notice that this first thing just cancels out to 0, this thing also just cancels out to 0 because this is multiplied by 0, and so this also cancels out, and it simplifies a lot. So that's why it seemed like we were just taking the simple integration, even when like this was mainly because of the cancellations, right? So yeah, finally we have proved this, and then now it's all easy. And I'm sorry for making this so complicated, but yeah. Yeah, so now that we have proved this claim that I made earlier, now let's get back to original integral and then complete it now. So we want to complete it, like it's been a long time. So 1 by n minus 1 factorial integral from a to x. We just realized that this entire expression over here is derivative with respect to g1 of a to g1 minus t to the power n by n f of t dt, right? And with respect to dg1. Okay, so now what I need to notice is over here there's some derivative with respect to g1, right? And we want to integrate that with respect to g1. So if we integrate some derivative, we'll just get this expression, right? So basically we are trying to carry out the outer like integral at this point. So our integral of this expression will just be this expression, right? So that expression will be our integrand, and the limits of integral will be from a to x, right? From a to x. So notice that we just carried out the outer integration without caring for the inner one. And now the substitute the limits of integration, and I can definitely take the n out over here. And if I substitute, okay, so this integration was with respect to g1, right? So this is from g1 equals to a to g1 is equals to x, right? If I substitute g1 as x over here, this will become a to x minus t to the power n by n f of t dt, minus, if g1 is a, from a to a minus t to the power n by, okay, n's already been taken out, so there's no n actually, 1 f of t dt. Now since the second integral is from a to a, that should be 0, right? So this becomes 1 by n factorial a to x, and then x minus t to the power n f of t dt, and the second one is 0, so that's just the answer. And I think that is exactly what we needed to prove in Pn plus 1 case, right? So 1 by n factorial a to x minus t to the power n. Yeah, so that's exactly what we needed to prove. Now, since p of n plus 1 is proved, assuming p of n, right? Assuming p of n, we proved p of n plus 1. Thus, by principle of mathematical induction, what you can say is p of n, this statement is true for all n belongs to natural number. And yeah, that proves the statement. So this proof is pretty powerful because we didn't really need to do all n integrals, just we did like one simple integral, and like that basically does the proof. So definitely proof by induction is pretty powerful. This formula is also pretty powerful. Leibniz theorem was also pretty powerful. Like everything, every idea over here was so powerful, and like the multiplier I was saying is also powerful. Everything was just dope over here, like pretty sick, yeah. And yeah, I definitely hope you enjoyed this formulas proof, and I definitely believe I'm gonna bring lots of videos where I use this formula to prove lot of other formulas. And yeah, this was awesome, no? Definitely share with your friends, definitely share with your teachers and professors. I believe everyone will like it. Just summarize, we used proof by induction, we proved the base case, and for proving p of n plus 1, we used p of n, and then we found out that actually we could integrate the outside integral before inner integral. For that, we needed to use Leibniz integral formula, and after that, we just integrated, substituted the limits, and that gave us the answer. So the only thing that took some time was using actually implementing the Leibniz integral formula for this case, because the variables got a bit messed up, but yeah, we did it. So that was it, guys. Hope you enjoyed the video. Thanks for watching, and I look forward to seeing you in like the beautiful videos that are about to come in this channel.